Okay, on 32, two ice skaters stand at rest in the center of an ice rink. When they push off against each other, 45-kilogram skater acquires a speed of 0.62 meters per second. If the speed of the other skater is 0.089 meters per second, what is that skater's mass? So, all these are going to be conservation of momentum problems. These first two problems are going to be kind of like when we had the two carts and we pushed the plungers together and then released them. Okay, total momentum before the collision is 0, so the total momentum afterwards still has to be 0. But there will be individual momentums afterwards. So on 32 here, just start with our full conservation of momentum equation. M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Now, both of them are at rest and they push off each other. All right, now sometimes it's helpful to draw a picture, just try to imagine what's going on here. Both start at rest, and then afterwards, they are going to be moving their respective different ways. This person this way, that person that way. Okay, so the entire left-hand side of this equation cancels out because they both started at rest. That's 0 and that's 0, so the whole side becomes 0. So we have 0 is equal to M1 V1 final plus M2 V2 final. We have the mass and velocity of the first person afterwards, and we have the velocity of the second person afterwards. Okay, so the first person is 45 kilograms. After they push off each other, moves away at 0.62 meters per second. And the second person, their mass is what we're solving for, is going to have a velocity in the opposite direction of 0.89 meters per second. Since that's the opposite direction, we're going to make that negative. Doesn't matter which one you make negative, whether it's that velocity or that velocity. No, what matters is that they're going opposite directions, and they have to have opposite signs. So, solving this for M2 here, 45 is 0.62 divided by, it's going to be a negative when we take it over to the other side, by negative 0.89. That should give us a final answer of about 31 kilograms. All right, moving on to number 33. Similar type of problem with a little bit extra thing to solve there at the end. It says the 92-kilogram astronaut holds on to a 1,200-kilogram satellite. Both are at rest relative to a nearby space shuttle. The astronaut pushes off the satellite, giving it a speed of 0.14 meters per second directly away from the shuttle. The astronaut comes into contact with the shuttle 7.5 seconds after pushing away from the satellite. What was the initial distance from the shuttle to the astronaut? So what you have going on here is, say, there's your shuttle. Okay, you have an astronaut here. All right, and then you have some type of satellite. Weird looking thing. So, push off the satellite. They want to know the initial distance that you were away from the satellite. Okay, now, all you have to do is solve a simple motion problem, your distance is equal speed times time equation, to that last step. The part that connects most of this chapter is finding the speed that he left with. So much like in the last problem on 32, both things were initially at rest. Okay? And they're floating in space, so there's no friction, there's no air resistance, and it's going to be a pure, conservation of momentum. They both had an initial momentum of 0. Afterwards, they're both going to have a final momentum of 0. So after the astronaut pushes off of this, you know what the speed of the satellite is, but we want to know what the speed of the astronaut is, applying, again, conservation of momentum. Now, they both start at rest. So just like in the last problem, the entire left side of the equation can go to 0 because they both start with a velocity of 0. You get M1 V1 final plus M2 V2 final. Okay, so let's call this the satellite and this the astronaut. You have those two values. You have the mass of the astronaut. Then you want to find the final speed of the astronaut. And then from there, you can just use that speed and this distance, or excuse me, that speed and this amount of time to find that distance. Just using, the speed equation is v is equal to d over t. So that means that distance is equal to speed times time. This is a last little extra thing there. Okay, so just plug in values. M1, a very large satellite, get pushed away at a very slow speed, 0.14 meters per second, plus the mass of the astronaut, 92 kilograms, multiplied by the speed that he is at, v2 final. Now if we set it up like this, that'll come out to be a negative number. That's fine. We should expect both of them, after they get pushed away, to have oppositely directed velocities. So one should be positive, one should be negative. If you make this one negative, that'll come out to be positive. It doesn't really matter as long as, the two wind up having opposite signs. So doing our algebra there, v2 final is going to be equal to negative 1200 times 0.14. Negative because you have to subtract it from both sides, get over to the other side, then divided by 92. So once we do that, we get our final velocity, which is about 1.83. 1200 times 0.14. 92. So 0.83 meters per second. Now just to double check, the satellite's very massive, the astronaut's not so much more massive. So we should expect this speed, and it actually comes out to be negative, we should expect this speed to be significantly higher than this speed, which it is. And it's nothing outrageous like 50 meters per second or something like that. So it's a very realistic speed, so it seems like a good answer. So the last thing we have to do in order to find that distance is just multiply your speed there. It's just a speed, so you don't need the negative. 1.83 meters per second times a time of 7.5 seconds, which gives us, when we take it to sig figs, about 14 meters. I guess to sig figs, that would just be negative 1.8. These are sig figs, 14 meters to sig figs. Should be good to go.